Welcome to the session of nonlinear optics. Nonlinear optics, abbreviated as NLO, is a branch of optics that describes the behavior of light in nonlinear media, that is, media in which polarization density responds nonlinearly to the electric field E of light. On the other hand, linear optics is a subfield of optics consisting of linear systems. If monochromatic light enters an unchanging linear optical system, the output will be at the same frequency. For example, if red light enters a lens, it will still be red when it exits the lens. In short, linear optics versus nonlinear optics can be understood as follows. Linear optics is optics of weak light, where light is deflected or delayed, but its frequency is unchanged. Here, we can see that the superposition principle holds good. On the other hand, nonlinear optics is optics of intense light. We are concerned with the effects that light itself induces as it propagates through the medium. Here, superposition principle is not valid. The nonlinearity is typically observed only at very high light intensities, such as those provided by lasers. Based on nonlinearity, let me introduce the concept of frequency doubling. Second harmonic generation, SHG, also called frequency doubling, is a nonlinear optical process in which two photons with the same frequency interact with a nonlinear material and generate a new photon with twice the energy of the initial photons. Equivalently, twice the frequency is half the wavelength that conserves the coherescence of excitation. Example: when light of frequency omega passes through a nonlinear medium, it gives rise to frequency 2 omega. We shall now see the two parameters associated with second harmonic generation, namely sum frequency generation and difference frequency generation. Sum frequency generation is a second order nonlinear optical process based on the annihilation of two input photons. This can occur only under conditions where light is interacting with matter which is asymmetric. For example, surfaces and interfaces. The light has very high intensity, typically from a pulsed laser. Sum frequency generation is a parametric process, meaning that the photons satisfy energy conservation, leaving the matter unchanged. That is, h cross omega 1 plus h cross omega 2 equal to h cross omega 3. A special case of sum frequency generation is second harmonic generation, in which omega 1 equal to omega 2. In fact, in experimental physics, this is the most common type of sum frequency generation. This is because in second harmonic generation, only one input light beam is required. But if omega 1 not equal to omega 2, two simultaneous beams are required, which can be more difficult to arrange. Some typical applications of sum frequency generation are generation of red light, that is red lasers, by mixing the outputs of a 1064 nanometer ND-YAG laser and a 1535 nanometer fiber laser. It results in an output of 628 nanometer. In such nonlinear crystal materials, sum frequency generation or difference frequency generation can occur where two pump beams generate another beam with the sum or difference of optical frequency of the pump beams. The nonlinear optic concept gives rise to Kerr and Pockels effect. The Kerr effect, also known as quadratic electro-optic effect, is a phenomenon observed in nonlinear optical materials, where the refractive index of the material changes in response to an electric field. This effect is observed in all materials. However, it is more prominent in certain liquids like nitrotoluene and nitrobenzene. In Kerr effect, the refractive index is proportional to the square of the field. Pockel's effect states that the induced index change is directly proportional to the square of the electric field instead of varying linearly with it. The Pockel's effect occurs only in crystals that lack inversion symmetry, such as lithium niobate, and in other non-centrosymmetric media such as electric field poled polymers or glasses. All materials show a Kerr effect, but certain liquids display it more strongly than others. In the next session, I will explain in detail the concept of wave mixing, third harmonic generation, and its application in optical image processing. Wish you a safe, healthy, and productive stay. Thank you.